Hi everyone, welcome to this week's lecture. This is actually part one of two parts for this week. So part one, we're talking about correlation. Be sure to check out part two where we introduce simple linear regression as well. But they're two kind of large and important topics, so I wanted to devote the proper time just to correlation, which is what we're going to talk about in this video. So an outline for today, Gersman's chapter 14 has 4 sections. The first 3 discuss correlation. So that's what I'm going to review here. There's also a supplemental reading from Dalgard, chapter 6. Section 4 is where he talks about correlation. He really introduces just some of the statistical output. Again, all the readings from Dalgard are just a really good way for you to familiarize yourself with what statistical output looks like, specifically from the software package R. So I definitely suggest browsing through that, making sure that you can pull out from the output the important things that we're going to talk about here today in this lecture. Section 4 also discusses 3 different ways to calculate correlation. I'm going to mention 2 of them in this video, but you can only do one of them in Excel. So if you ever need to calculate the other 2, then R is really probably your easiest way to do that. I'm going to do some examples, and then I'll briefly review the assignments for this week. Before we dive in, just like last week, I want to overview the general statistical procedure. Again, we always do exploratory data analysis first. We get an idea or build a picture in our mind of what the data is saying and how it's structured. We can then formulate our statistical hypotheses, identify appropriate tests, make sure that all the assumptions for conducting those tests are verified, and then we will actually follow our 10-step method to conduct the test. So we will be doing this again today. I'll be following all of these 10 steps as well as the previous 5 steps that you saw. So if you are not familiar with this by now, then please really practice. You don't need to memorize this necessarily, but make sure that you can reference it and you understand what each of the different steps mean. Especially as we start getting towards the end of the course, we're going to be using this every week, but this is really the foundation of statistical thinking and scientific thinking and the procedures that we're using for all the cool and wonderful and powerful tests that we are learning. So what is correlation? Well, we use correlation when we have 2 variables, 2 quantitative variables, and we don't know whether or not they're related to each other. And remember, the idea of 2 variables being related to each other is similar to the terms that we learned earlier in the course on dependence and independence between 2 variables. So we have 2 quantitative variables. We're not sure if they're dependent or independent. We want to test to see if the data disproves the hypothesized independence between the 2 variables, and we want to be able to describe that relationship if one actually exists. So I keep stressing 2 quantitative variables. Remember, there's basically quantitative and categorical variables. Now, there's also ordinal variables, which we learned about, but for the moment, let's just talk about quantitative and categorical. And remember, when we have 2 categorical variables, the best way to summarize data and see whether or not they are related to each other is with a joint frequency table. I really like putting a heat map on top of that just to get some colors to help show the patterns. Later in this course, we're going to learn a statistical test that can help us assess independence when we have 2 categorical variables. If we have 1 categorical variable but 1 quantitative variable, I really like side-by-side box plots. We learned how to do that, and we just learned last week that the statistical test we can use is an ANOVA test to test for means amongst several groups, and the groups is what is defined by the categorical variable. We also learned that if our quantitative variable isn't normally distributed, we have the Kruskal-Wallis test. So we have 2 different tests when we have 1 quantitative and 1 categorical variable to see if the variables are related. Today we're going to talk about when we have 2 quantitative variables. So this is correlation. The symbols that we use is the lowercase Greek rho. I know it looks like a P, but that's actually the Greek symbol for rho, and that's the symbol for population correlation. We use the Latin letter R for sample correlation. So just kind of like how for mean, we use the Greek letter mu for population mean, but X bar for sample mean, or the lowercase Greek sigma for population standard deviation, but the S for sample standard deviation. We have a Greek letter here for the population parameter and just a Latin alphabet letter for our sample estimates. So rho for populations, R for sample correlation. And the main or the most common correlation coefficient, or the way to calculate or measure correlation, is called Pearson's correlation coefficient. Pearson's is really popular. It's used almost all the time. Very few people probably know that others exist, but it assumes that the variables on which we're measuring correlation are normal. So again, this normality assumption, we've been seeing that this entire course basically. On all the t-tests, they all assume normality. ANOVA assumed normality. Last week we talked about what we can do when the normality assumption doesn't hold. So just like with the ANOVA, calculating Pearson's correlation assumes normality. It assumes that both of our variables follow a normal distribution. It actually assumes bivariate normality, but let's leave that for now. The book mentions that. For now, it's as long as you can verify that both of the variables follow a normal distribution, that's good enough. What happens if that's not true? And there's another correlation coefficient, and I'll discuss that a little bit more later. One important note is correlation, is, at least in this way, Pearson's correlation only measures straight line relationships. Now, the book uses the term linear. I think this is actually kind of confusing because when we talk about linear regression, linear in that context actually means something different than a straight line. So Pearson's correlation coefficient can only be used for straight line relationships. And the book talks about this a little bit. So if you have a curve or a parabola or like an S curve, you can't use Pearson's correlation coefficient. There are other ways that you can calculate correlation, but it can't be Pearson's. And I mentioned the non-parametric equivalent, it exists. So what happens if our normality assumption fails? Well, then there's something called Spearman's correlation coefficient. That's the second most common method for calculating correlation. And Dalgaard does talk about Spearman. So if you, again, are in a pickle and your data is really not normal and you have to calculate correlation, the easiest way is to download R and follow the instructions in Dalgaard and calculate Spearman's correlation coefficient. Unfortunately, you can't calculate Spearman in Excel. That would be really wonderful. I didn't find a nice little website or web applet that allows you to calculate Spearman's easily. In this course, we're just going to focus on calculating Pearson's, but I want you to know that there is another course of options. There is this non-parametric option, Spearman, when our normality assumption doesn't hold. Okay, so then Pearson's correlation coefficient, actually all of the correlation, well, at least Pearson's and Spearman's, always fall between -1 and 1. So if somebody tells you, oh, the correlation coefficient is 2.3, they're wrong. It can't be. By definition, it always has to be between -1 and 1. So the negative numbers doesn't mean that it's weaker correlation. Weak correlation or no correlation is zero correlation. So -1 is actually very, very strong. It's perfect correlation, only it's in a negative direction. So what that means is if you have two variables, x and y, if as x increases, y decreases. That's a negative relationship. So then your correlation coefficient will be negative. If as x increases, y also increases, then your correlation coefficient is going to be positive. So the negative and positive sign on the correlation coefficient just indicates direction. It doesn't actually indicate strength or magnitude. Strength or magnitude is determined by how far away from zero your correlation coefficient is. So for example, a correlation of -0.8 is actually stronger than a correlation of +0.1 because -0.8 is further away from zero than 0.1. Even though 0.1 is greater than -0.8, again, the signs don't matter. All that the minus part of -0.8 says is that it's a negative relationship, a negative straight line relationship. But -0.8 is very strong negative correlation. +0.1 is weak positive correlation. So the magnitude is important, and again, don't get confused with the sign of your correlation coefficient and the magnitude. Magnitude does not depend on whether or not it's negative or positive. Magnitude is how far away from zero it is. In practice, again, so 1 or -1 is a perfect relationship. So this is absolutely and exactly a straight line. Anything anywhere close to 0.7 or 0.8 is actually quite high. And in practice, we tend not to see that. And if we do see correlation coefficients that high, either this is, a quite seriously strong relationship, or we might be overfitting. So that's something we'll talk about a little bit later in the next lecture when we talk about simple linear regression and overfitting a model. We'll talk about that next week too. But most of the correlations you see are usually somewhere between 0.2 and 0.5. So for example, IQ tests, there's a lot of strong cognitive models that have been built and predicated upon finding strong correlations that are somewhere in the 0.5, 0.6 range. So if psychometricians find two tests that are correlated with a correlation coefficient of 0.6, they say this is actually quite strongly correlated. Because in practice, that's what we tend to find, that most correlations range somewhere between like 0.2 and 0.6. So anywhere that 0.2, 0.3 is kind of like a moderate to slightly weak correlation. 0.4, 0.5, 0.6 is actually verging on quite strong. 0.7 and above is like, this is really strong correlation. And if you get correlations, 0.1 or so or less than that, positive or negative, then that's kind of a weak correlation. One other assumption is that the samples must be selected via simple random sample. So we've been seeing that every single week. Again, that's true this week as well. And just like in the previous weeks, this is not a do or die situation. If the sample was not from a simple random sample, but was still from a probability sample, there are techniques that we can use to ameliorate the situation, but we're not going to get into that this course. One important note, very, very important, is that correlation is not causation. The book talks about this. You will see this and hear this all the time. This is kind of an in vogue statement to make. The image that you're seeing here is from a website that I really like called Spurious Correlations. You can find the website. The link is on the bottom right. Tyler Vagan or Vigen, I apologize for pronouncing the name incorrectly, .com. And you can more or less find correlations between all kinds of things. So this graph shows that the number of people who drown by falling into a pool and the number of films that Nicolas Cage appear in any given year are actually quite strongly correlated. But that doesn't mean that we should stop Nicolas Cage from appearing in movies, or at least we shouldn't stop him because we think he causes people to drown. If Nick Cage appears in 8 films next year, we're not going to think that, oh my God, because Nick Cage appeared in so many films, lots of people are going to drown. That's probably not the case, right? But this is the importance between correlation and causation. Statistics and statistical analysis on its own will never be able to determine causation. We can only determine correlation. This is similar to the idea of why we fail to reject a null hypothesis, but we don't claim that the alternate hypothesis is true. Statistics is really good, and quantitative analysis is good for building a prima facie. Prima facie is Latin for on the surface. You see this a lot in legal context, but building a prima facie case for something. And all that means is that we have evidence, and this evidence suggests that something may or may not be true. But then we need to follow that up with other investigations. So when we're doing correlations, we say, we have some evidence that these two variables, they appear to be related. We don't know if they actually are. This could just be coincidence. We don't know if they're causal or not. Even if they are causal, we don't know which one causes the other. But it certainly looks like they are related to each other. So we should study this more. And that's pretty much as strong of a statement that statistical analysis will ever be able to tell. So this is very important. I've been giving this feedback in a lot of your homeworks. Some of the statements that you make are too strong. Statistics doesn't definitively show anything. Same thing with really any science. We don't definitively show anything. The strongest statement that we can make is that, we have a lot of evidence. This evidence appears to suggest that this pattern seems to exist. So it might sound very wishy-washy, but that's because it actually is, because statistics cannot determine causation. We can only determine relationships. We have to go and, as humans, do some other further analysis to try to decide on causation. And that's where debates come in. So usually when somebody writes a paper and they say these two things, one of these things causes the other, people will not argue that there wasn't any correlation. They'll argue that the authors decided on the causal relationship incorrectly. So be very careful. Again, correlation is not causation. Whenever we identify statistically significant correlations, really all we can say is it certainly appears, or we have a lot of evidence that suggests that these two variables are related to each other. And that's as strong a statement that we can make. Okay, how do we calculate correlation? So this equation that I'm showing you, it's different than the one in the book. I think that this is the easiest way to calculate correlation. I'm going to use this equation later on when we do an example, and I'm going to show you how it works. Now, there's three new symbols here that you haven't seen. So x bar and y bar, you know, those are the averages for our two variables. So we're always calculating correlation between two quantitative variables. So there's this term in mathematics called without loss of generality, WLOG. All that means is that I'm going to use the symbols x and y, but it's really just any two variables. They don't actually have to be called x and y. They could be called L and V or P and Q, or you can call them Brian and David. It doesn't matter. But we have two variables. X bar is the average of our variable called x. Y bar is our average of the variable called y. In the denominator, we see x bar squared. So that's our average for x squared, then also y bar squared. And we have three new terms. This is xy bar. What this means is take all of your x's and take all of your y's and multiply them by times each other, and then take the average of all of those. We also have x squared bar. So as opposed to x bar squared, this order makes a huge difference. So this time, as opposed to taking the average and then squaring it, square all the values of x first, and then take the average. Same thing with y squared bar. Take all the values of y, square them, and then take the average. And all of you know what the square root symbol means. I think the more common or more popular equation that you see is the second one, which is that the correlation coefficient between two variables x and y is equal to the covariance divided by the product of the standard deviations. That being said, again, if we're going to calculate it by hand, I really like this equation. I think it's the most straightforward. So that's the one I'm going to use. You can also use the Coral function in Excel. Now you do need to be able to do this by hand. So I'm going to be doing it by hand. We will use the Coral function in order to validate the answer that we get by hand. Make sure that we didn't make any errors, but on your homework, be sure to calculate it by hand as well. After all, this is a class that counts towards your mathematics requirements. Okay, related to correlation is this idea of the coefficient of variation. So the coefficient of variation is equal to r squared. So the correlation coefficient squared. And it explains the percentage of the variance in one variable that can be explained by the other variable. So this is particularly useful when there is an explanatory variable and a response variable. So if we have a response variable, we can calculate the variance in the response variable, right? And if our coefficient of variation is 0.9, then 90% of the variance in this response variable can be explained by our explanatory variable. So that's quite strong. So a high coefficient of variation basically just tells you, you know what, we can actually predict with quite high accuracy what the response variable is going to be. So it varies because it's different, right? But we can explain a lot of this variability. So if it's really high, well, yeah, okay, that was really high, but it's because this explanatory variable was equal to this. And so when the explanatory variable is equal to this, response variable is going to be high. You say, oh, okay, it kind of makes sense. So we'll do an example of this. We'll do an example interpreting this. Basically, the higher r squared that you have, that means the better that you are potentially able to explain your response. But remember that correlation does not imply causation. So how does that affect coefficient of variation? Well, we will still make this type of statement that the percentage of variance in one variable can be explained by the other variable. But it's really just on the surface. We don't know if this is true or not. So again, you need to kind of quantify this. Say, it certainly appears that, or at least in our data, which is a good sentence to use so that we avoid extrapolation, which extrapolation basically means that if I have a bunch of data, then all my statistical analysis, I can only use that analysis and the results of the analysis to speak to my data. If things in the real world are slightly different than my data set, then all my analysis would also be slightly different, and therefore it's kind of invalidated. So extrapolation means that you can't use the results of your statistical analysis to describe anything that's different from your actual data set that you used. So we say that in our data set, approximately 45% of the variance in our response variable appears to be able to be explained by our explanatory variable. So some statements like this. So just A quick review of tests for normality. Remember the correlation coefficient, the Pearson's correlation coefficient assumes bivariate normality, or essentially just means that if we're calculating the correlation coefficient on two quantitative variables, that both of those quantitative variables need to be normally distributed. So here are some tests. Again, Shapiro-Wilks is what my go-to would be if I'm doing a test. But in this class, we are focusing on using QQ plots and theoretical versus observed density plots. And with that, let's dive into an example. It's example 14.16. It's on sodium and systolic blood pressure. So we have data from 10 individuals in all with renal failure, and we have the sodium in milligrams, it's the salt consumption, and we also have the systolic blood pressure in millimeters of mercury. And so let us do, basically it's part A and B. Really just part A on page 376. So we're going to create a scatter plot. We're going to calculate our correlation. But remember, in order to calculate Pearson's correlation, we have to verify normality. So we'll be doing that. And then we'll also calculate the coefficient of variation. So I'm going to do this live. Let's dive over to Google Sheets. So I really like Google Sheets. I've discussed in another video the statistics add-on. I think it makes life a little bit easier. So you can do this in Excel or really any other software you want. I'm going to walk you through doing it in Google Sheets, which again is free. So I've already entered in the data. So we have the sodium in milligrams, sodium consumption, and we have the systolic blood pressure in millimeters of mercury. And the very first thing I'm going to do is I'm going to create a scatter plot. So the way I do this is I calculate my two variables. I insert a chart. This isn't a scatter plot though, so I have to change this chart type, and it's this option, which gives me a scatter plot. So this is my scatter plot. Now the axes maybe need a little bit shifting around, which, let's see if I can figure this out. All right, I'm not going to waste time trying to figure out the axis, but play around with the axes. All the data points are here at least. So this is our scatter plot, and it certainly looks from a scatter plot that there does appear to be a positive correlation, maybe like a weak positive correlation. The data does kind of look like it's moving upwards. As sodium increases, blood pressure also increases. What I really like to do is to include a trend line. So if you click on Customize over here in Chart Editor and then Series, there's an option for trend line. And let's stick with linear trend line for now. A linear trend line is similar to the simple linear regression that we're going to talk about in part 2. And we have an option to show R squared. So R squared is 0.459. So it's not telling us the correlation coefficient. Remember, R squared is just the correlation coefficient squared. So we can take the square root of R squared, and we find that the correlation coefficient is 0.677. So that's actually kind of strong. And we only have 10 observations, so and it looks like there is quite a bit of variability here. But now we have a scatter plot. We have done our exploratory analysis. We have calculated correlation. We'll do this by hand again later. But it certainly looks right now that there is a relationship between blood pressure and sodium. And that relationship is a positive linear relationship or straight line relationship. And it's got a moderately strong correlation. So here's my scatter plot. And if you don't remember the steps of what we need to do, that's okay. And especially when I start doing the statistical test, you can look back to the steps. So I said, first thing, we're going to create a scatter plot. Maybe even before that, I want to go and see what are my 5 general statistical procedures. So first is perform exploratory data analysis. Okay, that's what we just did. Formulate a statistical hypothesis. We just did that. That's what we said. It looks like the data is correlated. It's got a moderate positive relationship. Then it's identify appropriate statistical tests. So we're not going to do a test right now, but let's calculate correlation. Before we can calculate correlation, we need to verify normality. So let's do that. And we can verify normality again in Google Sheets. Let's do this one variable at a time. So this is with the statistics add-on. We're going to describe the data. And we have the option to include the histogram, density, box plot, and the normal QQ plot. So that normal QQ plot is the one that I'm going to use to assess normality. So just looking at sodium, well, the density plot doesn't look very normal, but there's only 10 observations. So the QQ plot's going to be more informative. And well, we have these kind of two observations here that are well below the mean and two up here that are slightly above. But the group in the middle looks relatively close to that straight line. So, okay, maybe this is not overwhelming evidence to suggest that this data is not normal, but these two outliers are a little bit concerning to me. But I'm going to run with not rejecting the null hypothesis that this data is normal. So I don't think that this is strong enough evidence to suggest that this data is not normal based on my interpretation of this QQ plot. And then you can see some of the other pieces of information from this, the descriptions, but the QQ plots was important. Okay, so we think sodium probably follows a normal distribution. Now, so let's do the same thing for blood pressure. Variables. And the density plot looks pretty flat. Platykurtic, if you remember that term. Remember mesokurtic, it means the kurtosis equal to the normal distribution. Platykurtic is flatter than that. Leptokurtic is steeper. I think the book maybe discussed how the one way to remember platykurtic is platypus have flat tails, therefore platykurtosis is a flat density. Okay, let's take a look at the normal QQ plot. Okay, this is actually, all the observations appear to be quite close to this straight line. So that's good. This is actually less concerning to me than the normal QQ plot for sodium. So blood pressure certainly looks like it follows a normal distribution, or rather, there does not appear to be enough evidence to suggest that blood pressure does not follow a normal distribution. Remember, this is how we frame our null hypotheses and statistical analysis. So our null hypothesis is that the data is normal, and we fail to reject the null hypothesis. So there is not enough evidence to say that blood pressure is not normal. So with that, I think that both sodium and blood pressure probably come from a normal distribution. At the very least, there doesn't seem to be enough evidence to suggest that they don't. So let's calculate correlation. Let's do this by hand. And I'm going to refer back to this equation. So I need a couple things. I need, all of these are different averages. I need the average of X. So X is sodium. So I have all my sodium measurements here. So let's calculate the average. You can use the average function. If you want, you can also sum them all up and divide it by the number of observations. I'm not going to do that though. So the average of all of the sodium observations is 7.13. Similarly, the average of all the blood pressures is 172.6. So this is our X bar and Y bar. What else do I need? I need X, Y bar. So I have to multiply all of the X terms times the Y terms and then take the average. Okay, so sodium times blood pressure. This is going to be my XY. And I just take sodium times blood pressure. So for the first patient, sodium levels were 7, blood pressure was 156. 7 times 156 is 1092. So I do this for all 10 patients. And then I take the average. So my XY bar is 1233. Okay? That's this term. What else do I need? I need X squared bar. So I have to square all of the X terms and then take the average. So sodium was my X, so sodium squared. I will take sodium, multiply it by itself. So 7 squared is 49. And then take the average. Similarly, I have to find Y squared bar. So BP squared, which is the blood pressure levels for each patient squared. I'll do this for all 10 patients. and then find the average. So now I have x bar, y bar, I have xy bar, x squared bar, and y squared bar. And these are the 5 terms I need for my equation. So the first thing, the numerator is xy bar minus x bar times y bar. And let's do this side by side, actually. Okay, xy bar, so let's just do the numerator first, is xy bar minus x bar times y bar. Okay. And then the denominator. The denominator is a little bit more confusing. So let's split it up. Let's do part 1 and part 2. Part 1, and this is all going to go inside that square root sign, is x squared bar minus x bar squared. So x squared bar is here, the sodium level squared, minus x bar squared. So x bar times itself. Same thing. The second part is y bar squared minus, or sorry, y squared bar minus y bar times itself twice, y bar squared. Okay, then I have to multiply those two together. So I have this x squared bar minus x bar squared, that's 0.08. I have y squared bar minus y bar squared, that's 236. Then I multiply them together, and then I take the square root. So let's multiply, whoops, I screwed up my equation there. So let's multiply part 1 and part 2 together. And then I take the square root of that. And this is my denominator. And then I just do numerator divided by denominator. So my numerator was 2.952, my denominator was 4.3, and I get a correlation coefficient of 0.677. And let's verify that with what I got earlier. Yeah, 0.677. Now these numbers are a little bit different because I only got r squared at 3 decimal places. So this will only be accurate to about 2 or 3 decimal places, which indeed it does match up. So hopefully this was an example that helped you to follow this equation and calculate r squared. Remember, you have 2 variables, x and y. You then need to multiply them together to get x times y. You need to square each of them individually. So we have the x values all squared, the y values all squared. Then we have the averages for each of these different 5 variables, and we plug that into the equation. So I think that this is the easiest way to calculate correlation by hand. And again, I've split it up to do the numerator, then the denominator in 2 parts, and then slowly combine them, and then numerator divided by denominator. So if you have any questions about that, please do let me know. I can definitely do this. Do some other examples, and let's very quickly use the Coral function. So the Coral function is in Excel, but it also exists here in Google Sheets. So we use Coral, and then we have to select our 2 variables. So the X data and the Y data, and that matches up exactly with what we calculated on the long way. The correlation coefficient is 0.6777. So how do we interpret that? Well, again, so it's positive. So we have a positive straight line relationship, and 0.67 is quite strong. It's because looking at the graph and there's only 10 observations, I would say that this is a moderately strong, bordering on just a normal strong relationship. And the words that we use, moderately strong, quite strong, very strong, those are a little bit subjective. I think that's why we use numbers, because if you just say R equals 0.677, then that's what R equals to. And so if you have an understanding of what R equals 0.677 means, then you can interpret it, and that communicates the magnitude of the relationship. That being said, if you're just learning about what correlation is, you probably don't have that intuitive understanding it, so it's just going to take a lot of practice. And as you calculate correlation on data sets and do more statistical analysis, then you'll get a larger database of different correlation coefficients and the different strengths of relationships and different magnitudes of relationships in your head to which to compare. So I think 0.67 is moderately strong, or quite strong. Okay, so we have now calculated correlation. We verified normality. First, we looked at the QQ plots, and then we calculated correlation. So on your homework, make sure that you create these QQ plots. You include them on your homework. You say, I wanted to calculate Pearson correlation coefficient, but Pearson assumes bivariate normality. Therefore, I had to verify that my two variables are normally distributed. Here are the QQ plots, which show that there is insufficient evidence to suspect that the variables are not normal. Therefore, I can calculate Pearson's correlation coefficient, and I have done so. This is how I did it, and it is equal to 0.677. Okay, so remember, you need to show me. So if you can't just say, yes, the two variables are normal, so I can calculate Pearson's. Show me why. Show me the evidence that says or proves that treating the variables as normal is okay. Okay, let us now go back to our example. We wanted to do one last thing and calculate the coefficient of variation. So we have the correlation coefficient. Coefficient of variation is just r squared. So we multiply the correlation coefficient times itself, and we get the r squared coefficient of variation is equal to 0.459. And that's what Google Sheets had already told us, 0.459. And this means that approximately 45.9% of the variance in one of these variables is explained by the other variable. So now which one causes the change in the other? Well, we don't know. Statistics doesn't determine causation. Remember, so I don't know if it's that sodium can explain 45.6% of the variation in BP, or if it's BP can explain 45.9% of the variation in sodium. Now, knowing the little bit I do about physiology, I would say that sodium is more likely to explain BP than the other way around, but statistics in and of itself cannot say this. We need other pieces of information, other analyses to help interpret the statistical and quantitative output. So for this class, we would just say that the coefficient of variation is 45.9%, and that 45.9% in the variability of the variables can be explained by their relationship. And that's what we would leave it as. We'll leave it to other people to actually add their interpretations and meaning and try to add their explanations and arguments for why they think one variable causes changes in the other. That's not for us to say. Okay, let's keep going in our lecture. So we have calculated correlation. We've calculated the coefficient of variation, but just like with everything, we want to do a statistical test. It turns out the test for correlation is a t-test. If we take our correlation coefficient r and divide it by the square root of 1 minus r squared divided by n minus 2, n being the number of observations I have, this will follow a t-distribution with n minus 2 degrees of freedom, which is great. We know how a t-distribution works. We've been using that. The null hypothesis is that the population correlation coefficient is equal to 0. The alternate hypothesis is that it is not equal to 0. Now, you can do one-tailed tests. We're not going to worry about that now in this course. And we're also not going to do tests where the correlation coefficient, or the null hypothesis of the correlation, is not equal to 0. But you can do that. We can test that the null hypothesis of the population correlation is 0.5, and our alternate hypothesis is that it's greater than 0.5. We're not going to worry about that. Right now, we're just going to test null hypothesis of the population correlation coefficient is equal to 0. That means the two variables are independent. I mean, we'll assess to see if there's data to suggest that they are not independent of each other. Now, two very important things with all tests. Remember, one is test power. This is quite difficult to calculate by hand, but the following website, whose link I provided, has a calculator that does this very nicely, so I will utilize that. I suggest you do too. And confidence intervals, the book also provides an equation. I assume that most of you looking at that equation are looking at it and thinking, oh my God, I hope I don't have to do this. The good news is you don't have to. It is complicated. I'm not going to ask or expect that of you. There are two websites that will calculate our confidence intervals for us. The first one, the psyctc.org, will do it for any confidence level. The Vassar Stats link will only do it for 95 and 99% confidence. Granted, most of the time we're doing 95 or 99% confidence, so that's okay, but I will be using the other site, the psyctc. So make sure that you bookmark these websites whenever you're doing these tests for correlation. And let us, with that, take our example, the 14.16, and let us perform a hypothesis test. Let's see if this is a statistically significant correlation. So the first step, what is our null hypothesis? It is that rho equals 0. Our alternate hypothesis is that rho is not equal to 0. And what actually is rho? Rho is just the population correlation. So this means that sodium and systolic blood pressure are not correlated to each other. And I kind of worded it in a way such that the opposite is going to have a double negative, are not correlated to each other, which is very different than they actually are correlated. Our underlying distribution needs to be normal. We already verified this. Remember, in order to calculate correlation coefficient, our two data sets have to be normal. So we've done this already, which is fine. The sampling distribution, this is going to be a t distribution with n-2 degrees of freedom. We have 10 observations, so 8 degrees of freedom, n-2. Okay. What's our confidence level? Well, you know what? We haven't been told the confidence level to use. So I like using 90% confidence. Let's just use 90% confidence because our instructor told us to. Test power. Okay, so let's actually use this website. And hopefully it brings up this link correctly. Okay. I usually use Chrome. I brought up an Internet Explorer, not that I'm plugging one or the other. So we just input 3 different things. So what is our sample size? Our sample size is 10. Our correlation, we already calculated our correlation. Let's go back to Google Sheets where we did that. It's this whole thing, 0.6777547483. Now, how many decimal places do you actually need to enter? I don't really know. That being said, it's not going to hurt if you enter more. I certainly would enter at least 4 decimal places, but that's just me. Okay, and what's our significance level? So our significance level is alpha. Remember, alpha is the opposite of confidence. We said that we're going to work at 90% confidence, so alpha is going to be 0.1. We leave the power blank because it's going to calculate the power for us. We just click on calculate, and it tells us that the power is 71.5%. Okay, that's a little bit lower than what I was hoping for, right? 71.5%. So what can we do? Well, the 2 classic ways to increase power is to increase our sample size, but we don't have a choice for that. When we're doing t-tests, there was this difference worth detecting. Difference worth detecting is not part of the equation here. So the only course of action is we can lower our confidence. So what happens if we do that? Our sample size was 10. Our correlation was 0.6777547483. And maybe if instead of 90% confidence, what if we drop it to 85% confidence? What happens to the power then? The power goes up to 78%. Okay, so let's try it one more time. Maybe if we drop it even further, we drop it all the way to 80% confidence, then maybe what is the power going to be? 83%. So if we have 80% confidence or 80% specificity, we have 83% sensitivity. So that's the one that I like. It's got the most balance. So that's what I'm going to run with. I like to have tests again where we have balanced sensitivity and specificity. So if we drop specificity to 80%, sensitivity is 83%. Remember, specificity is the same thing as confidence or accuracy. Sensitivity is the same thing as power. So I know that I use the terms interchangeably, but I also want to stress the fact that there are these terms. They mean the same thing. Sensitivity and specificity are used a lot in biostatistics and public health. Confidence and test power are more general. So if you're not talking to somebody who's an epidemiologist, they're more likely to use the terms confidence and test power. If you happen to be talking to a public health analyst or an epidemiologist or a biostatistician, they're going to be probably using the term sensitivity and specificity. They all mean the same thing. Okay, so let's change specificity to 80%, and that way we have balance between our type 1 and type 2 error rates. And now, thank you to that website for helping us calculate power. Now we can collect our sample data and calculate the summary statistic. So we already have our data, but let's calculate our summary statistic. Our summary statistic is T. It's this test statistic right here. So let's go back into Google Sheets. Here is our correlation coefficient. This is what R equals to. So we need R divided by this whole mess. So let's do 1 minus R squared. I'm going to do this in parts. 1 minus R squared equals 0.54. N minus 2 is equal to 10 minus 2, or 8. So I have to divide 1 minus R squared by N minus 2. Then I have to take the square root of that. Then I have to take R divided by the square root of that stuff. So this is my test statistic. T is 2.607. And I can find the probability that I get a t-value more extreme. So I will use the t dot test. Actually, I won't use the t dot test. Let's do, I need to figure out which one of these values to use. And I don't see the equation here in Google Sheets. I'm very temporarily going to duck back over into Excel. I'm going to use the t.dist two-tailed function. My t-test statistics is 2.607114234. And again, you don't need to type in all 9 decimal places. I would do at least 4. I have 8 degrees of freedom, and Excel tells me that the probability p-value is 0.0312. P-value 0.03127. Okay, now I have my p-value, which is great. P here is less than alpha. Remember we said we're changing our specificity to 80%, so alpha is 0.2. P is less than alpha, therefore reject the null hypothesis. So it appears that we have sufficient evidence to suggest that our null hypothesis that the correlation between sodium intake and systolic blood pressure is equal to 0 is not true. That we estimate that the correlation between sodium intake and systolic blood pressure is approximately R equals 0.6777. Next, let's calculate a confidence interval. So again, I said this is kind of difficult to do by hand. So let us use this website. What we type in is 4 things. The sample size, which was 10. The observed correlation, 0.6777547483. And our confidence interval. Let's do our 80% confidence interval. I want 4 decimal places. And click Submit Query. And this tells me that my 80% confidence interval is between 0.3272 and 0.8639. So in 80% of confidence intervals for the correlation coefficient generated from samples of size 10, well, 80% of those confidence intervals will contain the true correlation coefficient. That's how we interpret it, right? But in practice, we say it's 80% likely that the true correlation between sodium and systolic blood pressure is between 0.3272 and 0.8639. Okay? And this confidence interval works the same way that all the other confidence intervals do. Again, use this website, these websites for power and confidence intervals. Power and confidence intervals are very, very important. It's just unfortunate that it's difficult to calculate by hand, but luckily there are these websites that we can use that simplify the process for us. Okay, let's go back to our slides. So we calculated the test statistic. Whoops. let me fill these in a little bit. So we calculate our test statistic. That was 2.607 or something like that. Our probability was 0.03-ish. Test results, P is less than alpha. Reject the null hypothesis. And then I kind of did the test summary out loud. That's where I talked about how we have sufficient evidence to suggest that the is incorrect. Okay, so that's all for this lecture. Our weekly assignments is we are working on the project again. There are 4 statistical tests that you have to do for your project. So it doesn't matter what data set you did, all 4 of the tests are the same. The 2 of them you need to do this week. The 2 tests that we've seen already is the 2-sample t-test for difference in means, and we just saw today the t-test for significant correlation. So you have to do both of those for your project. You have examples from the lecture. So today we did the t-test for significant correlation. Set it up the same way that I just did. Make sure that you have those 10 steps. Make sure you address each of those 10 steps. Make sure that you're doing your preliminary analysis. What you're going to submit is it's going to be similar to the problem sets, but submit each of these 10 steps. And I'm going to help you after this week formulate and display and communicate the results as if this was a report that you're doing for your job. So if you're working as a statistical intern for me, for example, this is the advice that I would be giving you. And in fact, this entire project, again, as I've previously mentioned, is designed like that. It's designed very similar to the relation that I might have with statistical interns that are doing work for me. Okay, coming up in the next couple of weeks, we have a problem set due next week on chapters 14 and 15. Again, what we talked today is chapter 14. So take a look at problem set 5. It's going to discuss correlation a little bit. Make sure that if you have any questions that you ask them. Week 12, then we have our quiz. Our quiz covers chapters 12 through 15. So it covers ANOVA, which we saw the 2-sample t-test, also correlation and regression, and then what we talk about next week, which is multiple linear regression. Just one note in particular as well, coming up in week 13, we do not have a Thanksgiving break, so we just have the normal 7-day week. I know that many of you do celebrate Thanksgiving, and it's a long weekend, and it's a time to spend with family and friends. We have a problem set due that week on chapters 16 through 19, which will be the lectures delivered in weeks 12 and 13. Please be sure that you are submitting your assignment on time. So take a look earlier in the week than you maybe normally do before Thanksgiving to try to do work on your problems. Try not to wait until the Saturday or Sunday when I'm sure you'll all be spending time with family and friends. Have a wonderful Thanksgiving though. But I also do want to make sure that you aren't missing all the deadlines. We only have 2 weeks left after that. So the course is coming to a rapid conclusion. And it's always a little bit difficult for these fall terms. Because we have Thanksgiving and then the rest of the holidays in December. So please just be sure that you're keeping up with your work and not falling too far behind. Quick review of what we talked today. We overviewed Gersman sections on correlation. We talked a little bit about Dahlgard and Spearman's in particular. Be sure that you are familiar pulling out Spearman's results, the correlation coefficient from our output. We review the 5-step and 10-step procedures that I've been discussing whenever you're doing any statistical analysis. We did an example. We calculated correlation by hand. So please be sure that you translate that equation. So the one with x y bar minus x bar times y bar. I really think that it's useful if you take that equation. You don't even bother writing it down in the mathematical symbols. Just for each one of those symbols, break it up and write down what it means to you. Write it in your own words. You can use English if you want or something else, but explain it to yourself and then use your explanation as the equation. You don't really need to go back to these other symbols. Really, whenever I go and I'm looking at different equations, I'm always translating into how I remember, how I interpret them. And I do this a lot with other things. So even if I'm like reading or if I'm reading some papers on psychology, I always translate them in a way that makes sense to me before I can do analysis on them. So you should do the same thing here. If the symbols are confusing to you, translate it into words or sentences or phrases that make sense to you. And then you can use that equation, your own, that you've explained in words that make sense to you when you're doing your problems, okay? I'll also discuss the assignments. Remember, though, that this is just part 1 of the lecture. This week, we have a lot of material. So correlation and regression are 2 huge topics. So this was a kind of long lecture. There's a whole other part 2. So please don't forget to watch part 2 on simple linear regression as well. With that, have an excellent week.